So this example is a calculator example. So one of the things that we want to do, especially as we get closer and closer to the AP exam, is kind of learn when to use our calculator, when not to. And you know, if we have the calculator, then the general guideline is to use it. It's not always going to be useful, but if we have to do any kind of calculations or anything, we're going to do them in the calculator. All right, so it gives us essentially a velocity vector. And it gives us dx dt, and it gives us dy dt, and it tells us the position of the object at time equals 2. So it says write the equation of the tangent line to the curve at the point where t equals 2. So in order to do this, we are going to write it in point slope form. So we need the derivative. We need dy dx. And we need it at the point where t equals 2. So dy dx is just dy dt over dx dt, again evaluated at t equals 2. So that is just cosine of t squared, so that's cosine of 4 over sine of t cubed, and that's sine of 8, and then I'm just going to plug that into my calculator. All right. Keep in mind that we should be in radian mode. So when we plug that in, I'm going to round that off to 3 or 4 digits. I'm going to leave 4 here, so negative 0.6607, and then the tangent line equation is just simply y minus 4 equals the slope, negative 0.6607, x minus 7, because they told us that the point was located at 7,4 at that time. All right, I want to find the speed of the, well, it should be the speed of the object. Not speed of the vector. The speed of the object is just the magnitude of the velocity vector. So we're trying to find the magnitude of the velocity vector, and really we're trying to find the magnitude of the velocity vector when t equals 2. So that's just equal to the square root of the sine of 8 squared plus cosine of 4 squared. And again, we plug that into the calculator, round off to 3 or 4 decimal places. 1.1858 is the speed, which is again the magnitude of the velocity vector. Alright, so it asks us for what value of t between 0 and 1 does the tangent line to the curve have a slope of 4, and it wants us to find the acceleration vector at that time. So if our slope has a curve of 4, then dy dx has to equal 4, and we want to know when that's going to happen. So dy dx is cosine of t squared over sine of t cubed, and we want to know when that is equal to 4. I'm going to use my calculator to do that. So what I've done here is try to get that into a place where you can see it. I hope the glare is pretty bad there. I put cosine of x squared over the sine of x cubed. That's my dy dx. In y2 I put 4, and then I set my window. My x values can be between 0 and 1, and I know that my y values have to be at least 4, so kind of from 0 to 5 or 10 or whatever. I think I set it at 10 here, and you can see the graph here, and then if I just do a second calc, intersect first curve, second curve, guess, you can see here my 0.61648,622. Right. As I write that down on the paper, I'm going to round that off a little bit, but I really don't want to round it off in my calculations. So I'm going to go out to quit, out to the main screen, and then I'm going to clear this out, and I'm going to just to make sure my x value is still there. I have it there. We can either save it. The glare is really bad. We can save it into a variable, so we could stow into A or B or C or D or whatever we want to do. Or in this case, with this software, I can just cut and paste or copy and paste that when I need it. So I can just use it that way. All right. So I'm going to set this aside for a second. We want the acceleration vector when our t is equal to that value that we got. So that's 0.61648. And again, I'm not going to write down all the digits, but I am going to use them in my calculations when I use my calculator. The acceleration vector itself is the derivative of the velocity vector. So the velocity vector was the x coordinate was sine of t cubed. So I need cosine of t cubed times 3t squared. And then for the velocity in the y direction was cosine of t squared. So that's going to be negative sine of t squared times negative 2t. No, I'm sorry, negative sine of t squared times 2t. So that will give us a negative 2t sine of t squared. So now we're simply going to evaluate this, each of these, at our t value, which again is here in truncated form, but I'm going to use all the decimal places. So my acceleration vector, when I plug this into the calculator and use that value that I still have saved in my calculator, I get 1.1090 for the x value of that vector, and then negative 0.45739 as the y value of that vector. Lastly, it asks us again about the position of the particle at time t equals 1. So we set this up, or we set up something similar in the no calculator section. Here we're going to actually evaluate it. So the setup is the same. X of 1 is equal to the x of 0, which was 7. Oh, sorry, that was x of 2. So where we were located at time t equals 2 was 7. So we're going to integrate from 2 to 1. This is going to be the change in the position in the horizontal direction between t equals 2 and t equals 1. Right? And then right from there, we're going to plug that right into our calculator. And what we get is 6.7819. So you can see that the setup is very much like the no calculator section, except now we can actually evaluate it using the calculator. And y of 1 is equal to y of 2, which was 4. We were located at y equals 4 when t equaled 2, plus the change from 2 to 1 of the velocity in the y direction, cosine of t squared dt, and again we put that in the calculator, we get 4.4431. So the position at t equals 1 is, I'm going to write it as a vector, 6.7819, comma 4.4431.